We'll now look at exponential models, what they are and how they work. This is the basis of an exponential model, y of t equal to c e to the kt. This c value is a constant and is usually our starting position. Whatever we're talking about, it's where we start. K is called the rate constant. And if K is positive, that means we have an exponential growth function. We are growing. If K is negative, we have an exponential decay function, and our population is shrinking. Let's suppose we have a bacterial colony that starts with 200 cells, and after 1 hour, there are 450 cells. The fact that we're starting with 200 gives us this c value in our exponential function. However, we still need to find our rate constant, and we can use the rest of the information to find that. If I let t be equal to 1 hour, so 1, then on the right we would need 450. And now we can simply solve this equation. We start by doing 450 divided by 200 to get 2.25 equal to e to the k. We can then take the natural log of both sides. And when we do that, we get approximately 0.8109 is equal to k. Therefore, our exponential model says y of t is equal to 200 e to the 0.8109 t. Next, we want to know when will the population quadruple. So we want to know when it will be 4 times as large as it started. Since we started at 200, quadrupling would be 800. And we need to solve for t. We start by dividing by 200. We can then take the natural log of both sides. That gives us 0.13863 equal to 0.8109 t. And then dividing gives us 1.7 approximately. So our population will quadruple in approximately 1.7 hours. The next question we ask is when will it reach 2,000 cells? Now we want y of t to be equal to 2,000. We start by dividing both sides by 200 to get 10 equal to e to the 0.1809 t. We can then take the natural log of both sides. This gives us approximately 2.303 equal to 0.8109 t. And then we can divide, and we get approximately 2.84. So our population will be 2,000 cells in about 2.84 hours. We'll now look at a decay model. C14 has a half-life of approximately 5,730 years. We want to know how old a bone is that contains 27% of its original C14. Well, you may have noticed when we looked at our quadruple example, our final operation was to do ln of 4 over k, and in general we can do that. Our half-life or doubling time or anything like that is ln of how much we are trying to get to the population. For half-life, it's ln of 1/2. If I was looking at doubling time, I would have ln of 2. Quadruple time is ln of 4. we divide this by k to get our actual time. I can then multiply both sides by k to get ln of 1/2 is 5730k. And then from there, we can easily solve for k. And when we do, we get that k is negative 0.00012. We also want to know when it contains its original 27%. Well, normally our formula does need the original amount, and we don't have that here. However, we can just think of it in terms of percent. Originally, we had 100%, which would correspond to a decimal of 1. So 1 e to the k t is equal to, in this case, we have 27% remaining, so 0.27. Our first step would be to take the natural log of both sides. And when we do, we get approximately negative 1.309. We can then divide both sides to get a time of approximately 10824. So this bone is approximately 10,824 years old.